Good afternoon, ladies and gentlemen. I'm Zhao Xuyang, a master student from National Sun Yat-sen University in Taiwan. It's my great pleasure to make this presentation today. The topic of my study is investigation on the material properties of high entropy alloys composites, a molecular dynamic study. Now I will introduce my studies to you. And my outline has 4 parts. First, I would like to introduce why we are interested in the current topic and what we would like to investigate. Then our molecular status simulation model will be introduced, including the potential function and the flow chart of my research. And finally, we will tell what we will do next in the future. And here is the introduction. With the advancement of science and technology, the demand for new materials has also increased vastly, and metal materials with better performance are needed. However, traditional alloys have many limitations and cannot meet the needs of various fields. Therefore, new alloying concepts are needed to develop new alloys. In 2004, Ye composed a multi-component alloys called high entropy alloys. And HEA are defined as alloys with 5 or more principal elements, and each principal element should have a concentration between 5 and 35%. Besides principal elements, HEAs can contain minor elements, each below 5%. And as we know, BCC structure usually exhibits a high yield stress and limits ductility, and FCC structure exhibits lower yield stress and high ductility. Therefore, we are very interested in what happens if we combine these two structures. And as the figure shows that dual phase HEA provide better mechanical properties than single phase. And we can see the figure on the left shows that according to the experimental result, the material properties of the material can be further improved by judging the nail layer thickness. Therefore, in order to obtain materials with better mechanical properties, it is very important to understand the mechanism of the effect of nanolayer thickness on material properties. And here is our structure and materials we use in this study. And however, it's not easy to develop new HEA. According to experience, it takes a lot of time and cost. To try various formula combination and control the temperature, pressure, and process time. By using the molecular dynamics, mechanical properties of the new HEA can be predicted before the experiment, and the cost can be reduced. Therefore, in this study, we are going to simulate the mechanical properties of the dual-phase HEA, including 10 elements as figured on the right by molecular dynamics. And here we use the second nearest neighbor modified NBD atom mass sheet, as known as 2NeAm. Potential will be used. And because our HEA system has non-typical metallic bondings, for its specific structure and composition. 2N MEAM potential is suitable for modeling this kind of metallic bonds, result in its non-specific atoms composition. Therefore, we use 2N MEAM potential to simulate our OLED system. The form of the 2N MEAM potential is shown at the upper of the slide. With the consideration of electron density of second nearest neighbor atoms, it will improve the atomic energy description. And here is our flow chart of fitting 2N MEAM potential. At first, we will find the best density functions series sets for every single element. Then B2 binary areas and multiple systems are constructed by DFT calculation as a reference structures. And next, we will build the energy curve of B2 structure as reference data. And after fitting parameters by particle swarm of optimization and build target function with DFT calculation. And if all of the targets converge, proceed to the next step. And here is our chart. And after having the potential parameters, a reasonable HEA structure is also important. This study used by random exchange of atoms in Monte Carlo to find the structure with the maximum entropy value in the whole system. And here is the process of creating the HEA models. And we create FCC and BCC lattice first and make the elements position random. And next, avoid the same type of atoms appearing anywhere within the first nearest atom distance. And third, exchange different types of atoms through MC and compare target function until the lowest objective function is found. If all of target function converge, proceed to the next step. And here the figure shows the HEA model. And now we have an FCC and BCC model, HEA models. And so that we should do next is combine them. And first, we have to know what kind of interface relationship the FCC and BCC have in experiment. And we make FCC and BCC interface follow the KS orientation relationship, which is the most common in nature. And then the HEA system model is shown in a figure on the left-hand side. And the right-hand side figure shows the KS orientation relationship. And C is the structure we combine. And here is the stable stating and anime of combined two structure. We keep the system fixed at 300K and XY axis at 0 bar, and compress the structure on Z axis by 50 bar. And all the dimensions are reperiodic. And here is the animation. And then here is the process of tension. And same as the stable proceed. We keep the system at 300K and XY axis are 0 bar, and all dimensions reperiodic. And we make 3 different layer thickness to find out the relationship between the thickness and mechanical properties. And we make 3 different layers thickness, 5 nanometers, 10 nanometers, and 15 nanometers. And here is the stress strain curve and the atom fraction figures of 5 nanometers, 10 nanometers, and 15 nanometers. And we found that when the thickness less than 5 nanometers, the curve of the stress strain and atom fraction are smoother. And the sudden drop and peak didn't happen. And here is the common neighbor analysis of 5 nanometers, 10 nanometers, and 15 nanometers. We pick up some special points and show their structure. We found that BCC dislocate to FCP and FCC first. Then FCC start to dislocate to HCP. And here is our future work. We will complete and analyze the mechanism of tensor and make different FCC, BCC thickness ratio to find out how to get the mechanical property we want by adjusting the ratio. And last, we thank National Sun Yat-sen University and Ministry of Science and Technology of Taiwan. Thank you very much for your attention.
Good, thank you very much. Any questions? Okay, please.
Is there any effect of temperature on the mechanical properties of the colors?
We only make in room temperature. Yeah.
Would it be enough to characterize the mechanical?
We will do different temperature in the future. Yes, it costs much of time, so only room temperature now.
Other questions? Okay.
After finding optimal structure or optimal position of each atom, metal atom, after that, how can we make the alloys in reality in that position, optimal position?
Yes, okay.
Through the simulation, we can find the optimal position of each metal atom, right? Then how can we make the same thing in reality?
Tough question. Okay. I have a question. When it comes to mechanical properties of materials, we have 3 types of tests we can perform: tensile, compression, and shear. And could you predict the other mechanical properties using simulation? I think you did only tensile strength, right? What about other shear or compression?
We can make the melting point thermal. Sure. Yeah. We only make the tension now, and we will have shear and thermal in the future. Thermal analyze in the future.
Okay. Thank you. Thank you. In honor of oral presentation, I'm going to deliver this. Okay, thank you.